Last unit was on electricity. When we finished writing our unit test, we went on to magnetism, and we talked for a couple of days about just basic magnetic effects. But largely, this unit has not been about just magnetism. Largely, this unit has been about the interaction between electricity from our last unit and magnetism. We learned very early on in this unit that a guy named Hans Christian Ørsted, almost 200 years ago in 1819, discovered the first relationship, and that is that the electric current produces magnetism. We could find the direction of the magnetic field produced by a moving charged particle by the Wire-Grasp rule. Sometimes they call it left-hand rule number 1. It went thumb in the direction of the particle, fingers in the direction of the field. Okay, done. Let's say in that first hand rule, in the Wire-Grasp rule, that we had a charged particle, a negatively charged particle going into the page. Thumb, fingers, magnetic field would point counterclockwise. Make sense? Well, then we moved on and talked about the coil rule. In the coil rule, we said that it's kind of similar to the Wire-Grasp rule, but kind of different to the Wire-Grasp rule. It's similar in the sense that you're using your fingers and your bent fingers, sorry, your thumb and your bent fingers, but it's different in the sense that you're swapping the roles of your bent fingers and your thumb. In this case, instead of being thumb in the direction of the particle, fingers field, it's fingers in the direction of the particles and thumb points in the direction of the field. So in this case, we'd say, look, my current is going from the negative side to the positive side. It's going clockwise around this coil here, around this solenoid. We'd stick our fingers up in the front. That would mean our thumb would automatically point to the right. That means that inside the coil, the magnetic field is pointed to the right. This would be the North Pole. This would be the South Pole. Again, Wire-Grasp rule, okay, thumb, fingers. Coil rule, fingers, thumb. Now, the third rule that we learned, we call the hand rule for deflection. Still dealing with interactions between electricity and magnetism. We learned that as a charged particle was moving through an external magnetic field, it would experience a force. And it experienced a force because we have the external field caused by the magnets. We also have a new magnetic field that's generated by the moving charge. Those two magnetic fields interact with each other. There's a force. What's the direction of the force? Well, hand rule for deflection says thumb in the direction of the particle, fingers field from north to south, my palm would point out of the page. So we've got 3 different rules here. First rule, when you're trying to find, quite simply, the field caused by a moving charge. Okay, the second rule, when you got a coil and you got a current and you're trying to find the polarity of that coil. The third rule is when not only do you have a moving charge making its own magnetic field, but you've also got an external magnetic field and a force as a result of those two fields. Now, a couple days ago, before we did our activity, we learned one more thing that's related to this rule, the hand rule for deflection. If we have not a charged particle moving through a magnetic field, but rather we've got an entire wire. Now, the wire's not moving through the field. The wire's stationary, but the wire has an electric current moving through the field. That's not going to be any different than a bunch of electrons just moving through the field. Okay, I could draw a diagram like I did here. Actually, let's reverse it here. I could draw a diagram like I did in number 3 there, where the charged particle is moving to the right. Okay, I can draw a diagram where we have a wire with a current moving to the right. Or I could kind of combine them and say, hey, look, this wire is just really a bunch of negatively charged particles moving to the right. All of those charged particles that I have in my 4th diagram here experience a force in the same way as the particle in the 3rd diagram. Thumb in the direction of the particle, fingers from north to south, palm points out of the page. Now, this particle down here, as it's deflected out of the page, will travel in a circular path as long as it's exposed to the magnetic field. These particles in this wire, they'll be deflected out of the page, but they won't travel in a circular path. Anybody tell me why? Why they won't go in a circle? No, not so much. Because in the end, if you didn't hear that, Cole said, because they're only being deflected for a certain time. Well, really, they're being deflected for as much time as this guy is, right? Assuming they're the same two magnets, the same strength of magnetic field and so on, then they're being affected for as long as that one is in diagram 3. Why in diagram 3 does it like to go in a circle? In diagram 4, they're not going to go in a circle. Yeah, they're in a wire. They're physically kept in a straight line by the rigidity of this wire. They can't go in a circle anymore, right? They want to, but they can't because they're not free to move around wherever they want. So they're going to be forced outwards still, all of them. But because they're inside this wire, they're going to drag the wire along with it. The wire is going to experience a force out of the page as well. So in diagram 3, the particle experiences a force out of the page. In diagram 4, the wire itself experiences a force out of the page. Now, we can describe this force by QVB. We can also describe that force by mv squared over r. We can also describe that force by Fc equals Fm because the particles go in a circle. This one we're going to describe by another equation. F is equal to ILB. This force is not the force on the individual particles. That would still be QVB. This force is the force on the wire itself. What's I stand for? Yep, current. Good. I stands for current measured in amps. L stands for the length of the wire. The length of the wire that's exposed to a magnetic field. If you have a 10 centimeter long wire, but only 8 centimeters is part of the magnetic field, then we only use 8 centimeters. If we have a 10 centimeter long wire and it's all in the magnetic field, but 4 centimeters are parallel to the magnetic field, then we're only going to use 6. Okay, we only want to use the part that's in the magnetic field and perpendicular to the magnetic field. Okay, always going to be measured in meters though. And B, of course, is the magnetic field strength. Make sense? All right. Okay, let's take a look at 2 questions that we had for homework that were assigned on Monday. And then we'll take a look at worksheet number 13 that was assigned on yesterday. Page 605 first. Any issues with this one? Nope. Number 2 didn't bother anybody? Well, we're going to do it anyways, whether you like it or not. Number 2 says a thin conducting wire 0.75 meters long has a mass of 0.06 kilograms. What's the minimum current required in the wire to make it float in a magnetic field of 0.15 Tesla? Hey, there's one word here I don't like. That's the word minimum. I don't like that here. Okay, I don't think it's well used at all here. Okay, I think that, in fact, I know it's not well used at all. It's not a minimum current. If you have below that current, it won't float. Okay, that's true. You got to have that current. You can't have below that current or it won't float. But if we have above that current, it's not going to float either. Right? If we want it to balance, then it can't be a minimum current. It's got to be a very specific current, not just above that current. Does that make sense? So we're going to actually scratch that out. We're going to say what's the current required in the wire to make it float in a magnetic field of magnitude 0.15 Tesla. What do we do? Yep. Good. Fm is equal to Fg. If it's not going up or down, the upward force has to equal the downward force. Fm is equal to Fg. We're going to say ILB is equal to m times g. We're going to solve for not the minimum current, but the current, mg over L times B. So it becomes 0.06 times 9.81 divided by 0.75 times 0.15. Make sure when you do the division here that you multiply the bottom inside brackets. And when you do that, we should end up getting 5.2 amps. Is that okay? Good there? All right. Let's take a look at our worksheet. Worksheet number 13. We'll put some answers up for that. You can go through it and see which ones you need to go over. And then we'll take a look at a couple of those questions. We got 1, 2, and 3 up there right now. Have a look. And the answers to 4 and 5. All right, we got a request to go over question number 2. We got a request to go over question number 3. So let's go over number 2 here first. It says the magnetic force acting on a wire is 0.030 newtons, has a current of 1 amp, has a length of 20 centimeters. What's the strength of the magnetic field? Okay. We circle centimeters because, hey, we forget to convert a lot. Okay, that's why they do that on the diploma exam. They put centimeters a lot because people forget to do that. and they seem to like to penalize people. They seem to like to take marks off of people. That's not what it is. They don't want to take marks off of you. They want to see if you remember you got to be in meters, right? And if you don't remember, then they're going to take marks off you. Okay, we got to remember that. We got to circle that to draw attention to that. We've got a force. We've got a current. We've got a length of wire. We're looking for the magnetic field. So we're going to use the equation that we learned on Monday, I should say. F is equal to ILB. We'll rearrange that to solve for B. The I and the L go down by dividing, so it becomes F over I times L. Let's say the force is 0.03 newtons divided by the current of 1 amp times the length of 0.20 meters. Now, the denominator this time is good. Okay, you don't need to worry about multiplying inside brackets because in the end, 1 times 0.2 is just 0.2. 0.03 divided by 0.2 would be, I'm going to say 1.5, 0.15. 0.15 newtons. Is that okay? Who asked me for number 2? Good? Did I make a mistake? Oh, sorry. Sorry, we're looking for magnetic field, so it should be Tesla. You're right. Newtons would measure force, right? Good, thank you. No, no. But let me qualify that. The question was, guys, if on a diploma exam, on a written response on a diploma exam, we said 1.5 times 10 to the minus 1, would we get it wrong? The answer is a qualified no. It's a correct answer, absolutely correct. But it's qualified because we don't actually have written response on the diploma exam, right? We've got multiple choice and numerical response. Now, you might have meant numerical response. If you meant numerical response, it depends upon how they asked it to be expressed. Okay? If they just said the magnetic field strength is blank Tesla, then the answer you would fill in would be 0.15. If it said the magnetic field strength is A decimal B C times 10 to the D or B times 10 to the W or whatever, Tesla, then you'd have to fill it in using scientific notation. Okay? It does matter, though. Okay, it does matter. You can't just fill it in any way you want, but it's not necessarily going to be my way. It just depends upon how they ask it. 3, calculate the initial acceleration of a 50-gram, 20-centimeter long wire. Okay, that carries a current of 0.6 amps if it's exposed to a magnetic field of 0.5 Tesla. The initial acceleration. What do we say in physics 30, 99 times out of 100, at least, that you're going to do when you're looking for acceleration? Yep. Good. A is equal to F over M, Newton's second law. Okay. There might be that odd time when you find A by using delta V over delta T or something like that. But the first thing that should come to your mind is F is equal to M times A. There's a lot of forces in physics 30. Odds are, if you're looking for acceleration, you're going to get one of those forces, and then divide that force by the mass. So let's get the force. If we need to if we need to go A is equal to F over M, we need to get a force first. It's a magnetic force, so we're going to say it's ILB. The current here is 0.600 amps times 0.20 meters. Didn't forget to convert that because I circled it. Times the magnetic field of 0.5 Tesla. 0.060 newtons is my answer for that. But it's not a final answer because I've got to find the acceleration, which is F over M, 0.06 newtons divided by 0.050 kilograms. Got to convert that as well. 0.06 divided by 0.05, I think, is 1.2, isn't it? 1.2 meters per second squared. Who asked me for that one? Is that good? Oh, okay. So you got 1.2? Oh, good. Perfect. Any more questions on that? I want you to have a look up here then and take a look at this electric motor that you see. An electric motor is a device that uses electricity along with relationships between electricity and magnetism to spin. Now, what's the purpose of that? There's a million different purposes. Maybe it's a hot summer day and you've got an electric fan in your bedroom to cool you down. That electric fan is an electric motor with fan blades attached to the armature. Okay, maybe you've got a toy car. Maybe you've got an electric car, like an actual electric real car. And you have a battery in that car, and that battery supplies an electric current and causes the armature to turn, which is attached to the wheels of the car and causes the wheels of the car to move. Okay, maybe you're baking a cake, and you turn on your Mixmaster, and your Mixmaster blades spin the eggs and flour and whatever else you put in the cake, and spins it around and beats the cake all up. Okay? The Mixmaster blades would be attached to the armature of an electric motor. Maybe you're not baking a cake. Maybe you're drilling holes in wood for something, building something. Well, the drill bit would be spinning around because it would be attached to an armature that spins in an electric motor. We're going to talk a little bit about the electric motor today, not because it's a direct curriculum objective, any more than the electrostatic fence painting was a curriculum objective, any more than the cyclotron was a curriculum objective. None of them are. They're all applications of curriculum objectives. Okay, the curriculum objective that's important here is sometimes called the motor effect. Okay, we didn't call it that the other day when we did it, but sometimes we do call it that. The motor effect is that phenomenon whereby you got a wire in a magnetic field, it experiences a force. Call it the motor effect because it's probably one of the most common applications in which the magnetic force on a wire is used. So how does it work? How does it work? Why are we doing it? Well, we want to expose ourselves to different applications, not because we're going to see them on an exam. If you happen to see this on an exam, well, you kind of won the lottery. Okay, there's a million applications that I could give you. There's a million applications that they could give you on the exam. Okay, if we happen to pick the same one in the same semester, you get lucky. It's not likely to happen, but it could. It's still useful to go through because it develops our mind. We're able to better understand. We're better able to work through novel applications ourselves with the more applications we go through in class. So, how does it work? How does it work? Well, there's a few main parts to this simplified electric motor here. Okay, the first part over here is just a little circuit. We've got a negative terminal of a battery, we've got a positive terminal. The electrons will flow this way, clockwise through this system. Now, they flow through this wire clockwise, and they get to this thing called a brush here. This brush is usually thin copper wires, like really, really thin, a whole bunch of thin copper wires. It's kind of like, you know, that big broom you use to sweep out your garage, except copper wires, thin copper wires instead of these bristles. So this brush made out of these thin copper wires is touching, but is not connected to this commutator. This commutator is free to move. The brushes aren't. The brushes stay where they are. So it's touching it. It's able to make an electrical contact, but it's not actually connected to it. It's kind of like we walk past each other, we brush hands. Okay, we touch hands, but we're not actually holding hands. Okay, we're able to still move past one another. As they're in contact with each other, the electrons will flow through the brush. Okay, they're going to flow through this commutator, and then they're going to flow into this thing right here that we call the armature. And it's going to flow clockwise through that, back around to the other side, back around to the other side of the commutator, through the brush, and then back down through here, back to where they started. We got an electric current flowing clockwise through this system. So what? Well, I'll tell you so what. As the electric current flows through a wire that's exposed to an external magnetic field, it experiences a force. There's a whole loop of wire here with an electric current in it. We don't really care, by the way, about this part of the wire and about this part of the wire. Anybody want to take a stab before we actually look at the part that we do care about? Why those two parts aren't important? Yep. Good. They're parallel to the magnetic field. There's no force acting on this part and this part because they're parallel to the magnetic field. Now, they got to be there to physically connect this part of the wire to this part of the wire. But other than physically connecting those two parts of the wire together, they're irrelevant in the whole deal. Okay, generally, what you're probably going to do is minimize the length of those two parts of the wire that are parallel to the magnetic field. Because all you do by increasing the length of this wire and this wire is weigh it down, make it heavier. You're not actually accomplishing anything useful by making those longer. Make these short wires. These wires, on the other hand, you might want to make longer. We'll talk about why in a minute. Let's look at, we'll call this A, B, C, D. Let's look at wire AB, or section of the wire AB. That's got an electric current pointing into the page. Take a look at the paper I have up in my hand right now. Okay, I've got this drawn out. Okay, I got a wire A, B, C, D drawn out just like I do on the board, except it's physical. They're trying to do it in 3 dimensions. Okay, I find the easier way is to actually do it in 3 dimensions for real. We got an electric current going from A to B. We got a magnetic field going this way, towards the right. If we have a current going from A to B and a magnetic field going towards the right, then the magnetic force on wire AB is going to be upwards, right? So wire AB will be pushed upwards. Agree? Let's look at CD. Wire CD here. There's a current out of the page for this one, right? Goes around into the page, comes around out of the page. Thumb in the direction of the particle from C to D. Fingers, field, palm points downward. So AB is pushed up, CD is pushed down. There's what we call a torque on this. Anybody know what torque is? Torque is what causes rotation. Torque is what causes rotation. Let's open the door here. I can apply a force, let's say of 5 newtons by my finger on the door. I push on 5 newtons, push with 5 newtons on the door, close to the hinges. What happens to the door? It opens. But it's harder to open the door than if I push with 5 newtons over here, right? Agree with that? Same force, different torque. It's not the force per se that causes the rotation. It's the force that causes the torque in conjunction with the distance from the pivot point. The torque causes rotation. So if we're applying a force upwards on wire AB and downwards on CD, okay, then that causes a torque, which causes a rotation in this wire. AB goes up, CB goes down, like this. Agree? Make sense? Here's the thing, though. When it makes 1/4 of a rotation, this little split right here in the commutator is now in contact with the brush. It's not a conductor. So contact is broken. There is no current now. The current goes A, B, C, D until the armature is like this, until the armature is oriented vertically like this. And then there's no current. So there's no magnetic force now on the wire. But it keeps going because it has momentum. Right? It's moving because it has a force. Force stops, but it keeps going because it has momentum. Just like when you run out of gas in your car keeps going for a brief time because it has momentum. It keeps going past the 1/4 of a rotation point to this point. Now take a look at what we got. On the left side, we had section AB. Now on the left side, we have section DC. That make sense? The CD side of the wire is now on the other side. The AB side of the wire is now on the other side. So now we have DCAB. Instead of, look at the paper again, ABCD, the current's going DCBA. Now, the current is still going clockwise through this system, but clockwise means the current actually reverses in the wire. If it was going ABCD, clockwise means it's now going DCBA. So clockwise, but opposite way through the wire itself. That causes a force on wire, well, what's now DC, force on wire DC upwards, and a force on wire BA downwards. 1/4 of revolution, breaks contact, makes contact again as it goes through that 1/4 point. Now the current's going ABCD. up on AB, down on CD. So the left side of the wire, every quarter revolution is just moving because it's got momentum. But at other times, the left side of the wire is always being pushed up. The right side of the wire is always being pushed down. So the motor ends up spinning like this because the left side is always pushed up. The right side is always pushed down. Does that make sense? You'd attach to that the drill bit. It's not a very good drill bit, but see what I'm saying. It's supposed to be a drill bit. You'd attach to that the fan blades. You'd attach to that the mix master blades. You'd attach to that whatever it is that you're trying to turn, the wheel of your toy car, whatever it is that you're trying to turn. Now, one quick little question for you before we wrap that up. I can think of three ways to make this spin faster. Three simple ways to make this spin faster. Right, Kirsten? What's one of them? What's one of the ways? Go on. You could increase the current, yes. If you increase the current through this system, then what you're going to effectively do is increase the strength of the magnetic force. And if you apply a bigger force, you're going to make it spin faster, right? Listen, push on the door, okay, we pushed at different points, supplied a different torque. It's the distance from the pivot point that matters on torque, but it's also the force. Because if I apply a force right here of 10 newtons, right, at the hinge, or sorry, at the doorknob, I apply a force of 20 newtons, it spins faster. Bigger the force, faster it's going to spin. Bigger current is going to give me a bigger force. So current matters, yes. What else? What else? Yep. The length of the wire. Now be careful with that one. It's this length of the wire that matters, right? And this length of the wire that matters, not this length of the wire. So L matters, bigger length, okay, bigger force on it. Now, how would we increase the length of the wire? You could make the magnets wider, right, so that the wire goes like this. But what you probably end up doing, because the motor at some point just becomes too unmanageably big, you probably end up doing it this way. You end up having a bunch of loops of wire go around. So now what we've got is 3 times the magnetic force there because we've got 3 times the length. Okay. This doesn't matter, right? This doesn't matter, but we still have 3 times the length of the part that does matter. So length matters, yes. I told you guys that this part doesn't matter. That's not entirely true. On a magnetic effect, it doesn't matter whatsoever because it's parallel, right? Mark said earlier, it's parallel to the magnetic field, doesn't matter. But the longer that wire is, the further away from the pivot point the force is. It's kind of like pushing the door, right? Push the door at the hinge, push the door at the doorknob. The further it is away from the pivot point, the bigger the torque, right? Easier it is to rotate it. So longer this wire is right here, it's not going to affect the magnetic force, but it would actually affect this phenomenon of torque, okay, which is not really a physics 30 concept, so I wouldn't lose any sleep over that one. But it would matter. It would matter, just not for magnetic effect, that's all. What's the third thing that I'm thinking of? What's the third one I'm thinking of here? Yep. Yeah, use better magnets, use stronger magnets. If you increase the external magnetic field strength, then you're going to increase the force. Where does that all come from? The magnetic force on a wire is I times L times B. Increase any one of these 3 or combinations of them, and you're going to increase the magnetic force. Make sense? All right, we're done our new material for the day. We're just going to do a couple multiple choice questions just to fill in the rest of the class here. I want to take a look at multiple choice number 80 and multiple choice number 81 here. Don't bother submitting these. We won't worry about that because time is running a little bit short. Just do number 80 and then we'll take a look at it as a group here, okay? Let's take a look at this one now. I suspect that there's a number of you that are having a little bit of trouble with this. Okay, when I looked at this question for the first time a number of years ago, I saw this as a, oh wait, it's traveling in a circular path through a magnetic field. I saw this as a FC is equal to FM problem. How many of you guys started with the same thing, FC equals FM? Hey, listen, even though that's not going to give you the answer there, I'm absolutely fine with that. A, because that's what I did. Didn't work out, but that's what I started with. And B, because it's a valid concept. How many times have I told you, don't ever be afraid to try a valid concept. Don't ever be afraid to try a valid concept. What's the worst that's going to happen when you try a valid concept like this? You're going to end up with too many unknowns. If we go mv squared over r equals qvb, v's cancel, mv over r equals q times b. Hey, we're looking for speed. Great. Proton, got the mass, got the radius, got the charge. Oh, wait, don't know what magnetic field is. Two unknowns there. So it doesn't work for me because I have two unknowns. But it is perfectly valid. It just isn't going to work out for us. Okay, but that's okay because we didn't get the wrong answer. We recognized when we got this far that it didn't work out for us. So we try something else. What else could possibly apply besides F equals FM? Well, maybe we could try FM is equal to QVB, but that doesn't solve the problem either because we still don't know what V is, we still don't know what B is. One equation, two unknowns. FC is equal to MV squared over R? No, that doesn't help us either. So what else? What else seems to be in this question that might help us? Good, the kinetic energy. Okay, we're told the proton has this kinetic energy, 894 electron volts. Look, it's a kinetic energy equation or a problem. If I said a car has 10,000 joules of kinetic energy as it travels down the road, what's its speed? You guys would nail this. Okay, what's the difference? A proton has this much kinetic energy as it travels down the road. What's its speed? We're going to say EK is equal to 1 FMV squared. The 2 goes up by multiplying. The M goes down by dividing. Then we square root that. We just got to make sure we convert this to joules. 1 electron volt is 1.6 times 10 to the minus 19 joules. 894 electron volts equals x joules. So solve for the joules. Okay, solve for the joules of this. Plug that number into here. And then turn around and solve for the speed. Okay, 2 of these I can eliminate right away. C and D. Why did I eliminate those right away? I can't do this in my head, 2ek over m, but I know it's not C or D. How come? Because, good, they're bigger than 10 to the 8. They're bigger than the speed of light. So it's got to be either A or B. Now, which one is it? I'm going to guess A. Is it A? Yeah? Why did I guess A over B? They both could, either one of those could be right, but why did I guess A over B? Yeah, like 10 to the 7, that's possible to get as a speed of a charged particle. But 10 to the 5 is more likely. That's why I guessed it. Obviously on a test, you're not going to guess it, you're going to calculate it, right? Now, one final thing, 81, you didn't have a chance to do that, that's okay. In 81, that's when we're going to go back to this, which was our first thought for number 80 here. Make sense? All right, we'll wrap it up there today.